Now in this we are going to solve some questions for the quiz for chapter 5, which is DC load line biasing circuits. Okay, a signal that swings outside the active area will be clipped. Okay, you have to refer to the diagram in the slide where it shows how the signal will be clipped. When you choose the Q point, the quiescent point or the operating point, close to cutoff, what will happen, close to saturation, what will happen. In both ways it's going to be clipped, so B is the answer. Okay, for specific area that is going to be cut off, you refer to the slide. The next thing is a step voltage divider is one in which the maximum current will flow to the resistor R2 and the current into the base of the transistor will be minimum. Okay, so in that case loading effects can be ignored. For this also refer to the slide. Okay, it's explained there, and for this it's clipped, and here it is, the loading effects could be ignored. Next question. Question 3. Assuming a step voltage divider, you're going to calculate the emitter voltage. Okay, so this is the emitter voltage VE. Now what is VE? You have a voltage VB here and you have another voltage drop VBE. So VB minus VBE will be VE. Okay, so VE equals VB minus VBE. Now you have to calculate VB. So what is VB? VB is the voltage, the V Thevenin voltage, which is the voltage between point B and ground, right? So it's exactly across resistor R2, and by voltage divider rule it is R2 over R1 plus R2 times VCC. Okay, so R2 is how much? R2 is 10 kilo ohms, right? 10 times 10 power 3 divided by R1 plus R2. R1 is 20 kilo ohm, R2 is 10 kilo ohm times 10 power 3, and the whole multiplied by the supply voltage 15 here. Okay, times 15. Okay, now on the calculator, 10 divided by 30, right? 10 divided by 30 10 divided by 30 equals this times 15. This is giving you 5 volts. So that is VB, 5 volts. Next is now VE equals this voltage 5 minus VBE is always 0.7 volts. So you have 4.3 volts. VE is 4.3 volts. So A is the answer. Okay, A is the answer. The next question is asking you to find on the circuit. For the circuit shown, the DC load line will intersect y-axis at what? At IC saturation, right? For the DC load line, the first point IC saturation on the y-axis and VCC on the x-axis. This is VCE cutoff. These are the 2 points that joins the DC load line. Now the question is asking you to calculate what? IC saturation. IC saturation we want. IC saturation, what is the formula for IC saturation? You can calculate IC saturation using VCC minus VCE saturation divided by, in this case there are two resistors RC and RE in this line, in this circuit. So VCC minus VCE saturation divided by this resistance plus this resistance will be IC saturation. Okay, so RC plus RE Alright, so now let us put the numbers in the formula. VCC is how much? VCC is 15 volts. So 15 minus 0.2, 15 minus VC saturation is approximated to 0.2 always, divided by the value of RC is 1.8 and 1.8 kilo ohm. The value of RC is 1.8 kilo ohm and RE is 1.2 kilo ohms. It's 1.2 kilo ohm. So 1.8 plus 1.2 times 10 power positive 3. Okay, so this is 15 minus 0.2 is 14.8. 14.8 divided by 1.8 plus 1.2 is what? 3, right? 3. So 14.8 divided by 3 equals 4.93, right? 4.93 times this 10 power positive 3 goes up as 10 power negative 3, 10 power negative 3 amperes. 4.93 milliamperes is the exact answer. Let's see if there is 4.93 in here. The closest one you should select. 4.93 is 5 milliampere approximately, so we can select this. Okay, now this is the answer for question number 4. IC saturation we have calculated. Next is in here, if you Thevenize the input voltage divider, Thevenin resistance is what? When you Thevenize, this is like going to be brought this side and the Thevenin's resistance RTH. Okay, so by formula, just go by formula. RTH is what? R1 R2 over R1 plus R2, right? So therefore you punch in the values again. R1 R2, R1 is what? 20 kilo ohm, R2 is 10 kilo ohm. So 20 times 10 times 10 power 3 in here, 10 power 3 in here, so 10 power 6, okay, in multiplication. R1 plus R2 is 20 plus 10 and 10 power positive 3 is common, right? So 200 over 30, 200 over 200 divided by 30 equals 6.67. We can round it to 2 decimal places. 6.67 times this, out of this 10 power 3, like this gets subtracted, right? 10 power 6 minus 10 power 3, this is going to end up in 10 power 3 as the answer. 6.67 kilo ohms. Do you have it in the thing? Yes, you have. So B is the answer. Okay, so Thevenin's resistance. Next is what? For the circuit shown, what is the emitter voltage, right? What is the emitter voltage? Now VE is what? VB plus VBE. So we know VE is VB plus VBE. Okay, VB plus VBE. So it's going to be greater than VB. So this is correct, not correct. Less than is not correct. Next is less than collector voltage. It doesn't say anything about it. It is not going to be less than collector voltage. Both of the above not correct. None of the above is what is correct. If you had seen that it's more than base voltage, then we could have selected it, but now none of the options are correct. So D is the answer for question number 6. D is the answer. Next, here, next is the emitter bias. Here, see, the emitter bias is not good for linear circuits. It uses voltage divider input, requires dual power supply. That is the answer, all of the above. So C is the answer. It requires 2 power supplies. For 7, C is the answer. It requires 2 power supplies. Alright, next, this also go through the slides. Next is, with the emitter bias shown, the reasonable assumption for troubleshooting work is that the base voltage is 0.1, emitter voltage is 5, emitter voltage is -1, collector voltage is VCC. So as per the slides, when you go, you will see that C is the answer, correct. Emitter voltage should be assumed to be -1 volt for troubleshooting purposes. Okay, next is next question. Ninth question. The circuit shown is an example of base bias, collector feedback bias, emitter bias, voltage divider bias. Go by the formula sheet. In there I have shown the circuits, the biasing circuits. I've shown circuits plus the formula. Okay, so this is an example of base bias circuit. Okay, A is the answer. Ninth question. And 10th question, the circuit shown is an example of, it looks like the same like the previous circuit, but in the second circuit this collector resistor is left and this one is giving this collector is going to be connected to the base like that. It's a like this. It's a collector feedback bias. So B is the answer. B is the answer. That's it. We are done with the quiz.